phase space, let me read it, a combination of position space and momentum space. It is just the combination of these two spaces. And so the small element in phase space is denoted by d tau, and it's given by dx dy dz times dpx dpy dpz. Okay, that is phase space. Now the mu
Hmm.
space and gamma space, they are the two definitions of phase space. So let's
So
limit
what
ourselves to
is
the
the?
comprising one molecule for,
It
yeah.
would be better, I think, if you explain a little bit of what is mu and what is gamma and how they are different spaces.
I'll read it out, then we can
Okay.
better
Yes.
understand.
Sure.
Hmm? Let's let's limit ourselves to a system just which is comprising of just one molecule, and
Mm-hmm.
moreover, it's considered to be a monoatomic as the simplest system. We have a monatomic
Okay.
gas having one
Yes.
molecule only. The state of
Okay.
the gas is completely known. The position and momentum of each of the perfect gas
Mm-hmm.
is specified. We just want to know about the position and the momentum it has. That's all we want for any given gas, okay, for any
Mm-hmm.
given situation. The position of an atom can be specified in this rectangular coordinates xyz, and it's known as position space. And simply the momentum of an completely known if the rectangular momentum components px py pz are specified same. This is called momentum space. Now this six quantities for each atom, when known, the state of the gas can be determined. The state can be
Mm-hmm.
determined. Okay, the space covered by the infinite set of these six coordinates is called the phase space for a single monatomic molecule. So it can have infinite possible values because px, py, pz can be anything, and same
Mm-hmm.
as xyz also. Since the energy of a molecule is given by px square plus pyz plus pz square divided by 2m, that is
Yes.
nothing but the
Kinetic
kinetic
energy.
energy. You know it, yeah. Mv square equals given by no p square upon 2m. So
Mm.
the momentum space representation also gives representation of energy of the state.
Uh,
For having information of any state, we just want to know about its energy and the
mm.
particles residing in that system. Okay, so
Yes.
basically we are having that. If we are having the momentum, then we are having the energy also.
Mm-hmm.
Such a six-dimensional space of a single particle is called molecular phase space. Now, this 6D space for a particle is molecular phase space because or mu space.
Mm-hmm.
Six dimensional diagram cannot be drawn. Phase space is purely a mathematical concept. What we are trying to put here is that this whole idea of having six dimensions is a little bit, hypothetical. It can't
Mm-hmm.
be imagined in real sense. And this whole space for a given molecule is called as mu space. That's one thing. Okay,
Mm-hmm.
we'll talk about the gamma space also. Now suppose the position or momentum of one of the molecules is changed slightly. The phase point of this molecule will undergo displacement in the phase space, and the microscopic state of the gas will be modified.
Mm-hmm.
To explain it further, let's consider the mu space divided into a two-dimensional energy sheet having position coordinate x on x-axis and coordinate py axis. Okay, so let's subdivide the range variables x and px into arbitrary small discrete intervals called phase cells of arbitrary size. The minimum size of phase space cell is explained as under. So we have done nothing but
Yes.
we have put a
Mm.
two-dimensional graph here, है ना, having x and y direction. So as to get the simplest form possible. Hmm. That's just considering the
Mm.
x direction. So we are also, this sheet is, uh, you know, uh, cut into small pieces, very small pieces having some dimensions of very small magnitude, which we not know as of now. We'll look into what is that. Okay, so minimus now the block size, this phase cell need to be, defined that what it is, what does it reside there, and what dimension does it have.
Uh-huh.
So this is discussed in this paragraph. The meaning of a
Mm.
point in this phase space is well understood with the help of Heisenberg uncertainty principle. So this new thing is coming into picture. Let's see what it presents. Let dx be the size of the interval on the x-axis and dpx on the px-axis. Okay, the phase space is divided into energy sheets of smaller and smaller energy ranges. Smaller and smaller energy ranges. Mind it. dpx
Yes.
and dx when combined gives energy multiplied by time. So we are talking about nothing but energy. So this energy sheet thus consists of small cells equal to area dx into dpx, and the product of this we are telling it as h naught. Okay, the state of a system can be
Yes.
specified by looking at a phase point within a particular cell of phase space. In classical description, h naught can be chosen arbitrarily as small as possible, and we may set it as 10 to the power minus 30 second. Okay, that is a given value for this h naught here, so, or even smaller values. It may be noted that h naught has a dimensions of energy into time. Now, this thing is quite new to me at least, that this product is giving energy and time. Okay, so the lengths
Actually,
dx and
dimensionally, if
yeah,
you look at it dimensionally, then energy into time has the
yes,
same. Um, uh,
mm-hmm.
if you look at the unit of h, the Planck's
Yes,
constant.
yes,
What is the
yeah,
unit of Planck's constant? If you remember.
it's joule second. Yeah,
Yes. So in that case, you get a joule second thing, right? Here we call
yeah,
its momentum into x. Well, that is also going
mm-hmm.
to be dimensions of joule second.
Joule
Dimensions,
second.
mind you,
Yeah, this
dimensions of
coincidence,
joule seconds.
and I think this
And energy
this
into time, just a second, just a
yeah,
second. Energy into time is
sure,
going to give you a joule second, right? Dimensions.
right.
And
Mm-hmm.
angular momentum is also joule seconds.
Sorry.
Angular momentum is also a joule second, you know?
Okay, okay, angular momentum. Okay,
Yes.
yes, sure,
And
sure, yes.
this is
Mm-hmm.
how the conservation of angular momentum comes in the atomic realm
Mm-hmm.
when we talk about spins.
Mm-hmm. Hmm.
Tell me what you were telling me.
Yes, rightly said. And also adding to that, this H naught is, being, you know, invented here. I should say discovered here. This H naught quantity is discovered here only. I think, as it's written in later section of this book, that this given quantity is turned out to be, Planck's constant later on, and has got a perfectly fixed magnitude of the smallest value. I don't think there's any constant existing
You
which
know,
whose
hmm
whose magnitude is lesser than this. Do you think so?
I can't really comment on it because I don't think I'm qualified enough at this point. Um,
No, yeah, I know definitely we are not so much enough, qualified enough to,
because
put
in order
things
to
into
say whether or
straight
not this
sense.
is invented right here at this point in the development of physics or somewhere before this or somewhere after this, I haven't gone to history. Now, I would like
Mhm.
to, analyze this concept of phase space a little bit more. I mean, if you
Okay.
want to describe state of a system at a certain,
Hmm.
what are you going to do on this phase space picture?
Okay. 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 What do I think about this? Is
Yes.
that let's say in real, no, in normal life, in real sense of macroscopic objects, we have, you know a floor having some, area of 100, say 100 square feet. Okay, a floor of 100 square feet. Then we can have a, ball of 100-gram mass, and it can be, present anywhere in between the space. Okay, that thing is very real, normal, and we can analyze it through naked eyes. But for a given atom or given molecule, and that too when they are having such a great quantity as 10 to the power 20, 30 entities, then for them we need to, analyze them. Now that can't happen through naked eyes, that's right. But can we suggest a space, can we suggest a similar kind of thing, what we have in real life, that three-dimensional space we have in real life, say walls, we have, height, uh, length, and depth,
Let's
you
not go
can say
to three
height.
dimensions. Is it necessary? I mean, I just want to be it to be very, very simple. So one dimension I think is fine. A,
No, one dimensional is good. Okay.
a point is traveling on x-axis. That's it. You know, and you want to describe the state of that point at a given time using the
Yeah.
phase space, one dimensional phase space.
Okay. Okay, fine. So you see it will have some velocity, and
Very
it
good.
will have
And
some position. Okay,
yes, very nicely done.
definitely. Without this, except this, it may have some. you can say potential energy, it may have some charge. Let's say it may have some charge. It may have some electric field also, but we are not considering that, here. So what we are just considering about this, that okay, there's a molecule, it's running in one direction, it has got this velocity, that's why it has this kind of, sort of energy with it.
Let me take you a little more closer, because I am able
Yeah.
to see, and I want you to see the same way. So
Mm-hmm.
I mean, if I just put a point on this graph, what that
Right.
you tell me? Just one point.
One point, Shivam, won't define anything.
If you
Let me
look
tell
at
you.
this, if you look at this, on y-axis
Sure.
you have the momentum, an increasing order of momentum, and on the x-axis
Mm-hmm.
increasing order of position, right? So if I just put a dot right there,
Mm-hmm.
it's going to tell me
Okay.
the the position at a given time. Let's say it's x1 somewhere, measured from the origin,
Yes.
x1,
Mm-hmm.
and then the corresponding y value will tell me the velocity it has at that time, at that position. It's like a
Yes.
bike is moving and I suddenly take a snapshot, right?
Yes.
So
Right.
that snapshot tells me that where it is on the map, well, it is at a given
Mm-hmm.
position, and then it has
Mm-hmm.
velocity. That velocity is also seen. So don't you think a point on
Definitely.
is going to give me the position as well as the velocity of the system, right? At a given time, at a specific time,
Mm-hmm.
isn't it?
Mm-hmm.
Of course. Okay. Now,
Right.
now what you see here is a classical picture. In the case of quantum,
Mm-hmm.
things won't go as straight as in classical. So a
Mm.
point is simply an undefined idea. It is simply a nonsensical idea in quantum mechanics, because
Mm.
point means you have a certain value of position and you have a certain value of velocity, which is simply not going to be. I mean, you can't do that in quantum mechanics, right?
Yes. Yes. Yes.
Yes. So
Mm.
I think what will happen in quantum mechanics is, and what will happen in classical mechanics is, in classical mechanics you can make the value of h naught as small as possible. The smaller it is, the more precise the position and the velocity, isn't it?
Mm-hmm.
When you say that
Okay.
it is in a given particular phase cell, and I say that phase cell ki arbitrary
Mm-hmm.
ho sakti hai, it can be any value, any arbitrary value. So I can
Yeah.
make it as smaller as possible. The
Yeah.
smaller I make it, the more precise will be the position and and velocity, right? But in quantum mechanics, you simply
Right.
cannot do that. So what will happen is, uh, so what will happen?
Mm.
You can say in quantum mechanics that is going to remain the phase cells area is going to give you h, which is
Yeah.
Planck's constant. And if you
Mm-hmm.
try to shorten, I mean, if you try to, I mean, if it is this square thing, okay, if it is this square
Okay.
thing, perfect square,
Right.
okay, and what you do is you want to find, if you want to make the position variable as precise as you can, okay,
Mm-hmm.
then
Okay. Yes.
what you really do is you basically um, reduce the breadth of this. I mean, this point. How should I show this thing?
Yeah.
मतलब तुम
Okay. I'm getting the point.
इसकी चौड़ाई को तुम घटाओगे ना.
Definitely.
Yes.
Definitely.
अब अगर
Definitely.
तुम चौड़ाई
PH will
घटा
tend to
रहे हो,
zero.
अब अगर तुम चौड़ाई को घटा रहे हो, है ना? Then what will happen?
Yes.
Obviously, the position will be very very accurate now.
Yeah. Yeah.
Since quantum mechanics limits the value of h to a given quantity, it cannot be smaller than that. What will happen when you crush it? When you crush a given cell, ये ऊपर की तरफ ये फेंक देगा. It will become elongated. Don't you see? And there will be an uncertainty in momentum. Can you see that? What I'm trying to show you.
No. No. Your last two sentences were not clear. What you said that you are
What I'm
minimizing the
saying is,
px
yes,
to
yes,
zero.
yes.
Then.
What I'm saying is, this area which is h, if I limit it to
Okay.
a particular value, which is the Planck's constant,
Sure.
it cannot be
Sure.
smaller than that, right? If you crush this thing from minus x and positive n plus x, if you just crush it, plus s minus x direction से तुम उसको crush कर रहे हो, है ना?
All right. All right.
So what will happen is you're trying to minimize the area, isn't it? Make it smaller.
Definitely.
But since quantum mechanics limits it, the more you crush it from side by side, the more elongated it will become, because the
Definitely.
used to be,
Definitely.
and then
H. Yeah.
what you see is you have a very accurate value of position because you have crushed it, right? You have crushed a phase cell, which has got elongated, and then there's an uncertainty in momentum as well.
Yes, yes, yes. Very, very nicely put, Shivam. Very nicely put. I was thinking of that only. That dx into dpx is greater than equal to h kit, right?
Yes. Yes.
The product of this two should be greater than or equal to h kit. And here we are saying that in this classical mechanics, this mu space, that this small cells have an equal area, and that is that dpx into dx, and that is equal to h naught. So in this case, this h naught should be h kit, Shivam, right? And
Yes.
this is
Yes.
a
In the
very,
case
very
of quantum
particular case.
mechanics. Yes.
In case of quantum mechanics, and they have said this thing that okay, h naught can be anything, but Heisenberg now will tell, as you said very precisely, that okay, this equation is clear but not very clear. This equation should be equal to equal greater than equal to this left hand side should be greater than equal to h ket, and that h ket has this specific h value. Okay, that is
Ah.
6.6
Yes.
into the power minus
Yes.
34 joule second.
Yes.
You know,
Yes.
they have defined it very precisely, and
If
you
you
are
if you try
perfectly
to smaller,
right in this
if you
sense.
want to, if you crush the value of dx, the dx
Mm-hmm.
as small as you can for this
Yeah,
particular cell, there will be a huge spike
yeah.
in dpx, and so there will be an
DP, yes,
yes.
yes,
So what we see here is that phase cell
definitely.
can be used to state the position of a given system. And in classical
Mm-hmm.
mechanics,
Mm-hmm.
H naught can assume any arbitrarily small value, whereas in quantum mechanics, that is not the case.
Yeah.
H naught will be equal to H get, and it cannot be smaller than that. And the more precise the position, the more
Mm,
uncertainty in momentum, and vice versa.
definitely. And Shivam, you must remember you shared some videos of Brian Greene with me. They talk about space time, they talk about the universe, multiverse. In that one of the videos, the Einstein said that the world is you know divided into pixelated form. Everything is made of pixels, and that pixels have dimensions of h. The Planck's constant, the very small value they have. I just remember this thing, and that was really great. And he argued with people that I don't know the other scientist who was in the other way. He was saying that the world is very continuous. There's nothing like pixels. There's nothing like edges. Everything is very smooth and simple. But Einstein was stuck to his point, and what we say here now that Einstein was correct. Hmm? Things are actually pixelated. This thing actually an argument you can say, but as per our studies, we are quite near to the solution that okay, things are pixelated. So okay, one thing we saw here that okay, these small phase cells are there now for different sort of like classical mechanics. This different phase cell is defined differently, and in quantum statistics the phase cell is defined differently. Hmm. So okay, this equation is true. This dx and dpx equals h naught. This equation is true, but it changes its way. It changes its we can say the h naught value according to the statistics involved. Okay,
Yes.
right. Okay. Now minimum size in quantum statistics. Let's see. Okay, very same thing is written. We can glance it through it. This is erg seconds. So 10 to the minus 27 in joule second. It is 10 to the power minus 34 j as it is written joule
Yeah.
second. So okay, the volume they have actually defined the volume. Hypothetically, they can define the volume of a phase cell, right?
Yeah.
Because it's six dimensional, so they have multiplied all these values into each other, and got d tau equals h cube, and this h is basically Planck's constant. Okay, so this thing's done. Now we are coming back to the gamma space. My voice is clear, Shivam?
Yes, your voice is HD.
Okay. So here we have to deal with a system of n molecules. In mu space, we are dealing with only single molecule. So there's nothing new, just n is involved, and there are two alternative methods. One is to have the six-dimensional three position, three momentum space phase-space representation, and we take n points to represent positions and momenta of n molecules at a given instant. So there we had only 1 point because of one molecule, and same way we can have n. This thing is called mu space. Okay, having 1 point in that space is called mu space. The other alternative method is gamma space. What we do here is, it is a six-dimensional phase space representation in which a single point represents a state of entire n particles systems and is referred to the representative point. So instead of taking n different particles in six-dimensional space, we are taking a six-dimensional space and pointing a one particle. You know, these both the things are directing to the same destination, but are the path is different.
Explain me once
You
again.
getting? Okay, sure. So what we did there, we had a six-dimensional space. Okay, px, py, pz, and x, y, and z. Okay, and we just put a single point on that space and got the space of that particle, the position, the momentum of that particular particle, the single particle. That is the method called, this is the method used in mu space. Okay, we can have any number of particles and we can just put them in their respective momentum and positions points. Okay, then what we'll have that different set of positions and momentum for different set of molecules. In this case, what we are doing is we are having n molecules. Okay, n molecules, Shivam.
Uh-huh.
So instead of having a six-dimensional space and putting n molecules in n spaces, we are reciprocating this thing. We are just having a six n-dimensional space. Okay, six n-dimensional space and 1 point in it. So the product, basically the product remains 6n.
Uh, Unbelievably complex
Six
space.
n-dimensional. Yeah. This thing cannot be,
Never, never.
imagined.
It can never be imagined.
Yeah, never be imagined. I remember one more thing. I don't know how my memory is sharpened today, but in the very beginning of our session of, in fact, our college life, you were teaching something. I think statistical mechanics it was, and you were saying about three
Yes,
dimensions. Can you remember it?
yes, yes, yes.
It is August of
तो
2018.
याद है अरे
All
वाह
right.
मुझे लगा तुम्हें याद
So
नहीं होगा गुड
definitely,
yes I
मुझे
actually
अच्छे
taught
से
this
याद है.
chapter
Sure.
actually
So
I've
that.
taught this chapter in to Rani and Pranjal was
Hmm.
there and you were also there and I remember doing it and I have
Yeah.
photographs as well of that day so
Bilkul,
I just
bilkul.
needed
And
a bit of revision that's why
Mhm.
move on
And that at that time I was very new. I had just 2-3 days passed in the college, and I saw you were teaching this thing, and you were talking about six dimensions, and we had, like, I had the question like, how can you say about the six dimension? We are not sure about the four dimension as of now. How can you talk
yes
about six dimensions? I was totally astonished about the fact, and at that time I had no idea, and you tried to tell me, but I didn't had such great mind at that time to understand that concept. So now at this point of time, I'm getting this thing that, okay, six dimensions. Shivam, what do you think? This is hypothetical phenomena, right? This
it's
six dimensions having
it's a
px, py, pz.
theoretical convenience okay we can't imagine it of course we can't imagine it
Hmm.
but you know there is something that is followed and that something is this general rule so what is that general rule
Mm-hmm.
so the Pythagoras theorem it's in 2D base
Yeah,
square plus
definitely.
perpendicular square is equal to hypotenuse
Hmm.
square, right? Now, if I construct a
Hmm.
three-dimensional triangle, if you can imagine that, okay,
Okay.
a pyramid basically, yes. So in the case of pyramid as
Or a
well,
tetrahedron maybe.
yes, yes. So even in the case of a in that case, this Pythagoras theorem, in its more generalized form, is present in that case also. Okay, so if you want a three-dimensional,
Yes.
a three-dimensional counterpart of hypotenuse square, so there is a base square, there is a height square,
Mm-hmm.
there's a third side square, and then when you sum these three,
Mm.
you get the hypotenuse square in 3D.
Mm-hmm.
So this kind of uh,
Yes.
general idea, that if you have, let's say, you go to from 3 to 4 dimensions. So you have a square plus b square plus c square plus d square
Mm.
is equal to e square. This generalized form of Pythagoras theorem is. So what we say
Yes.
is, well, we cannot imagine.
Yes.
Definitely, we can't imagine 4 dimensions and higher dimensions. But mathematics
Mm-hmm.
can help us tackle,
Mm.
deal with higher dimensions. Despite our incapacity to imagine,
Definitely.
mathematics can help us deal with it. So
Mm.
this is simply a mathematical convenience
Sure. Mm.
to.
Basically, very rightly said. And also Shivam, if we think that okay, we are just providing we just want the information of any one particle, and that information we want to plot it in a graph in a dimensional space. So
Yes.
that's why we are doing, for the sake of presenting it easily. We are happening to draw a graph, we are happening to draw phase space in it.
Press
Hmm.
press S
Because
F
basically
F11
a
F11.
particle, any particle resides. Sorry.
Press F11 if you could.
Hello.
Yes, hello. Control F11.
Okay, 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 okay.
Yes.
Huh.
It's not working in your case.
Is it better now? Shall I zoom it?
F11. Do you have a function key right in
Is it
the?
full screen now?
Yes, it's full screen.
Yeah.
Yes. Okay.
Shivam.
Yeah.
I have shared my screen full. Yeah. Hmm. Okay, okay.
Now it's all right.
So, okay, just for the simplicity, mathematical
Uh,
simplicity, we are plotting it in simple form, like Brian Greene, talk about that space-time theorem, thing in such detail in such a small video of 1 hour. He
yes.
completed everything. Very great to see. So, okay, let me read this thing and you'll get the idea. So, the other alternative method, which is in gamma space representation,
I
we
think
have a
your screen
six-dimensional
is not
phase space.
visible.
Instead of, oh, is it so?
Yes, yes.
I haven't stopped sharing. Let me visible again.
Uh, share once again. Try sharing once
Is
again.
it visible? All right.
Stop.
Hello, Shivam.
Huh?
Can you see my screen?
No, not yet. At least. No. It is
I
actually
have shared
right
this.
in front of my screen. There is a sentence, a statement. Arpit Singh ASAS Lucknow has started sharing screen, but I can't see the screen.
That is precisely what has a. Okay, I have shared it. Let me do it
Yeah,
once
now
again.
it's okay. Yeah, now it's okay. Yeah, now I
Okay.
can see it.
Oh,
Now it's gone.
I have stopped sharing it, and you are saying. Now tell me.
Again, I'm waiting for.
It should be visible now, I think.
Yes, now it's visible. Good.
Yeah. Okay. So let's proceed again. Continue from the frame spot. We are talking about the gamma space, and we have this 6 n-dimensional space. For the mathematical ease, or for the mathematical options we have, we are just saying that okay, this is 6-dimensional space, and we have one point in it. Okay, and that one point can represent n particle system,
Yes.
and is referred to as the representative point. Now,
Yes.
this is in contrast to the mu space. Why?
Yes.
Which refers to only one particle. That is
In
one
six
point for one
dimension.
particle. But in 6-dimensional space, we have one point and we have one particle. So that was the
Yes.
case for mu space. Now, the gamma space representation is mathematically more difficult to handle. Why? Because it is six n dimensional. How can we think of that? But it has one great advantage, Shivam.
Uh-huh.
Have some emphasis on this point. If an ensemble is to be represented, this six n dimensional representation alone is applicable. If an ensemble is to be represented, this six n dimensional representation alone is applicable. Different points will then represent the corresponding all microstates of another macrostate. The gamma space is considered to be a conceptual Euclidean space having two Fn rectangular axes. Hmm. Now this thing should be clear to us that how the ensemble thing is coming into this picture.
It's not clear, really. Is it to you clear?
No. I'm pondering about.
So the ensemble's definition, according to this statement here in the book, it is assembly of all
Hmm.
microstates of the system corresponding to one macrostate. So of course there are
Ah,
certain a
yes, yes,
huge
yes.
number of total number of microstates to a given macrostate, but
Hmm.
then there are some
Hmm.
accessible and there are some who are not accessible.
Yeah.
And an ensemble
And Shivam, on. Okay.
is the
Okay.
one which is accessible, right? The set of microstates which are accessible.
Hmm. Hmm. Shivam,
Huh?
can we say this thing that the accessible microstates are the one where the probability of finding electrons or atoms is at least greater than zero, and the inaccessible are the ones where the probability is zero. You
Okay.
know,
Don't you
what do
think
you think about this
to
statement?
this definition at least?
Hmm?
Some in the book.
Wait. I have this definition of ensemble in this. I wanted to talk about that, and let's just move towards that only. This has this book has shown this thing very simply, very simple. It is easy to get this and understand, whereas the distinction is also very clear. Along with that, they have provided a use of it. So okay, we know that there are three ensembles,
Hmm.
and before that, I think yeah, I should read this paragraph. They will better make you understand that what is the use, what is the requirement of having
Yes.
an
Yes.
ensemble.
Okay.
Okay, so let me read this. In statistical mechanics, Gibbs introduced the concept of ensemble. It's obvious that a very large number of states of a gas corresponds to a given macroscopic condition of the gas. That means they are talking about the microspace. Microscopic condition lies inside a macroscopic condition. There are
Yes.
a number of microscopic conditions and are lying inside a given microscopic condition that is written here in this statement, because there are infinite number of ways to distribute the molecules in space. That's fine. Through macroscopic measurements, we could not able to distinguish between two gases existing in different states but satisfying same macroscopic conditions. um, if two gases are having same macroscopic condition, say same volume, same temperature, all in all, but you know we want to know about the microscopic conditions. Overall they are broadly the same, but are they same? Because they shouldn't be same. Why? Because they are two different gases. We need to distinguish between the two. So for that purpose, we need to know about the microstates as well. Hmm. The micros, the macrostates alone won't do much. So we are basically they are saying that we require a set of microstates which can distinguish and give us a more deeper information about the gases present, right? Thus, when we speak of a gas under certain macroscopic conditions, we are in fact referring not to a single state, but to an infinite number of states. So I'm getting at this thing. Please stop me whenever you feel anything confusing. Okay.
Okay.
So, in other words, we are referring not a single system, but to a collection of systems identical in composition and microscopic conditions, but existing in different states. So, okay, according to Gibbs, such a collection of systems is called an ensemble, which is geometrically represented by a distribution of representative points in gamma space. They are using the word gamma space too. We haven't used this term in any ensemble.
So
Instead,
far,
at
at
least
least.
I,
Yes.
yeah,
Sure, sure.
this thing is,
Same here.
yeah. So we are interested in finding the microstates of the gases. Okay, the microstates and what are the possible values of it, how many of them rely really are there, and what kind of attributes they have. So this is geometrically, this is geometrically. Gamma space is nothing, was the geometrical representations, the graphs, the six dimensional, six n-dimensional basically space. So they want to distribute this geometrically with points in the gamma space.
So you know what transition is happening here. I guess the
Mm.
transition that is happening here is the following.
Mm-hmm.
We are able to visualize a system of micro canonical ensemble, for example. Okay. So micro
Okay.
will mean
Mm-hmm.
there is a constant energy, constant number of
Yeah.
molecules, and constant volume. E, V,
Mm-hmm.
N. These three are constants. And we are able to visualize it in three-dimensional space, Euclidean space. Okay. By Euclidean,
Yeah.
it
Yeah.
means the Cartesian coordinate
Ah.
system sort of thing.
Yeah. Sure. Mm.
So we know the position. I mean, we have a box. That's what. And one of the
Mm. Yeah.
box is the origin,
Yeah.
right?
Simple. Simple.
Cartesian
Mm.
origin. Okay.
Mm.
So this is the something, and there is another visualization. And from the first one to the second one, the transition is happening. So I've described the first one. The second one is uh, the, the gamma space,
Mm-hmm.
and this is not simply
Mm.
a box with origin in one of the corners. No, it's not like that. Here the origin is something way more different, way more profound, and
Mm.
it is not straightforward.
Mm-hmm.
Y-axis is going to tell
Yes.
us position, the momentum. The x-axis is going to tell us the position, and a point on that space is not going to tell us. It is not going to show us the particle. Point is not a particle. A point is a state.
Mm. Definitely. Bilkul.
So
Bilkul
yeah,
sahi.
in the first visualization, a point is a particle, and the second visualization, the point is the state of the particle, and this is the transition that we are going through in this paragraph. I guess.
Definitely, perfectly pointed out. And to add this, this point will not only define the state of a single particle, but a set of particle which will be small n. Like we have said that, okay, in the energy E1, there resides N1 particles, and there are G1 number of quantum states totally, right? So
Yes.
by pointing a single point in this gamma space, we'll have that Ni, and for that we'll have all the possible you know uh, properties or the characteristics of those Ni particles. So just one point can give whole complete information for n particles,
Yes. Yes.
right? So perfectly pointed out. Now, this is what is an ensemble is, and we'll surely look into the differences a bit later. I should read this thing. Thus, an ensemble is defined as a collection of large number macroscopically identical, but essentially independent systems. By the term macroscopically identical, okay, we mean that each of the systems constituting. Shivam, can you wait for a minute? Just a minute, okay?
Sure. Sure.
Give me a minute. So from outside we'll see that, okay, these all this boxes, these macroscopic boxes, are saving the same, having same temperature, same volume, same number of particles. But when we'll dig deeper into them,
Uh,
then we'll find, okay, their some their velocities may be changing, their quantum states may have different energies discretely. Okay, also they are they are having transitions from one quantum state to another. These all things we'll come to know only when we dig deeper into this, right?
mhm. Yeah.
So these are the things. By the term independent systems, we mean that the system containing, constituting an ensemble are mutually non-interacting, just like the role of non-interacting molecules. That's fine. Okay, they are non-interacting. They have no interaction in between them. Now,
Mhm.
for these three micro, I should start with the micro canonical ensemble. They have defined it quite clearly and gave a little cute example, which we can have to understand it better. Now, this classification basically depends on the manner in which the systems interact, and it has its own characteristics distribution. Physical systems can remain perfectly insulated from each other, hmm, or can interact in a variety of ways, which we will discuss. In particular, they may exchange energy or matter or both. Let's see what they have to offer. Starting with the micro canonical ensemble. Okay, we know broadly, so I'll just read out, but we'll see what new thing it
Sure.
has. The microcanonical ensemble is a collection of essentially independent systems having the same energy, volume, and number of particles. We know that E, V, N is constant for each and every uh, micro canonical micro state, I should say. Hmm. These values are same. Wait. Hmm.
I have a
These
question.
all nine. Huh, yeah. I'm thinking of the same thing. I think you are. Okay, ask a question.
So in this figure, we see the
Hmm.
big box, and then there are nine
Yeah.
boxes, and each
Hmm.
small box has a certain EVN.
Hmm.
Means because I have been believing so far that the bigger box has this thing EVN as constant, and I haven't really bothered about thinking of the small boxes in terms of small boxes. I haven't done it yet, and this is a new revelation, I think, to me.
Hmm. Yes. Sure. Just I'm yes. I want to put these things very nicely, and you know these all nine small boxes, they are having the same as E, V, and N. All nine have mutually same energy, mutually same volume, as well as same number of particles.
Mm.
That means these are nine set of macro systems. You know,
Yeah.
these are nine macro systems inside which there lies many number of micro systems. In each of the nine macro system. So from outside, what we see that okay, these all maybe are having same quantities. They are same energy, volume, and number of particles. But as we dig deeper, we will come across that okay, they may have different set of quantum states, different uh, you know uh, energies in that different quantum states. They will have discreteness in them. That thing we can't predict from outside, right? So simply they are what they are saying is that okay, we have different macro states, but their characteristics are same. Their magnitude of characteristics is same. Still they are different. Why they are different? Because micro properties are different for them. Hmm.
Mm.
So this individual, the individual system of a microcanonical ensemble are separated by rigid, impermeable, as well as insulated walls, such that the values of E, V, and N for a particular system are not affected at all by the presence of other systems. So
So
these
in
are macro states. Are
this lining that we see
yes.
in the box, line, uh,
Mm-hmm.
so this inert material in on it,
Yeah.
so ensuring that the two boxes within will not
Mm-hmm. Definitely, sure. Definitely. These all are, you know, separated by this adiabatic walls, I should say,
Yes, adiabatic
because they
wall,
don't
correct.
allow,
Yes, right.
they won't allow any energy change or any matter
Yes.
change, nothing. Now, let's see that what's happening. So this they have given a little example based on energy. Now, considering a closed system for which the total energy H, Q, and P. Okay, energy and QP. That means they have it's defined between Q. Let's say um, it should be the basically it is a Lagrangian coordinate. Okay, which is not defined as of now. So this is some Lagrangian coordinate, but P is surely nothing but momentum. You know that thing.
Mm.
The momentum uh, is considered, as well as another coordinate Lagrangian coordinate Q is considered. Function, the energy is a
Generalized
function of Q and P. Generalized coordinate. Yeah, very rightly said. Generalized coordinate in Lagrangian. Hmm. And in Lagrangian mechanics, we use that. Okay, we have studied well. So the energy E is constant. Now, according to the equation, E function of Q1, Q2 till Qf, P1, P2 till Pf equals constant. We are considering a system in which the energy and the set of which is dependent on the generalized coordinates is constant. Now, the locus of all such points which have equal energies in phase space is called an energy surface or ergodic surface.
क्या
Now,
क्या
this
what
thing
was
is,
this?
yeah,
So,
yeah. I'll read it out once again. The
yes, yes.
locus of all such phase points having equal energies in phase space is called an energy surface or ergodic surface. So I will make this thing more clear. Like Shivam, just assume like in this graph we have this Q in the x direction and P in the y direction. What they'll do is they'll form a circle. Concentric circle will be formed
Mm-hmm.
on which, on the perimeter, all every perimeter at every point, the product will be same. The P into Q will be same.
Mm.
You know, the product will be same. So they are all having equal energies in phase space.
I don't think the
Okay,
P
this.
and Q will be same. Will it be? Because I think because mm, because when we talk about a circle, we talk about uh, x square plus y square is equal to constant, isn't it?
Yes, Shivam.
So the squares of these coordinates, p square and q square, when we add them together, we get something that is constant. And I think this is what is described here. Don't you think so?
Okay, that's fine.
Because circle
And
x square plus y square is equal to constant.
definitely, Shivam, definitely. But you see one thing, the
Hmm.
Q, the Q is not defined here. What is Q?
In a
Can you say
phase
of that?
space, because it's written right down in down in the figure, it's
Hmm.
figure 10.5, energy shell in
Okay.
space. So when it's saying it's a
Mm-hmm.
phase space, then by definition we have to assume that q is nothing but position variable in a generalized form.
Hmm. It should have been. Uh, why did they put a Q in that? Okay, that, yeah, that your point is making
Because we are
sense.
yes, because you know what, because we are considering energy not as a constant but as a function of something, you know
Hmm. Definitely,
whenever
sure.
we do
Definitely.
whenever we talk about energy as a constant value, right, we say it's E,
Mm-hmm.
capital E or something like that. But when we say that energy is a function of something, then we replace the technical term energy by Hamiltonian. When energy is a
Sorry,
constant, we say
sorry.
energy. When energy is not a constant but a function of something, we replace the technical
Mm-hmm.
energy by Hamiltonian.
Hmm.
And that is why whenever we consider Hamiltonian, we have to consider generalized coordinates. So I think this is nothing but position versus momentum graph.
Okay. Yeah, yeah, yeah. Your argument is very fine. It is in phase. with what we have studied. And
Yes.
yes, we must assume Q as X. Okay, this is
Yeah.
position, Q is position, and P is momentum. Okay, that will be fine, because the product of that will give same arguments as we have studied in this session. Now, okay, let's not consider this as a sphere. Let's just consider that it is a surface, Shivam. Okay, surface, that means there should be a line. Okay, in two dimensions should be a curve. Okay, as depicted in this, like there's a, it's an arc basically. Okay, this is a arc. Now for the whole arc, the energy is constant at any given
Yes.
point. The product of these two will be constant. Okay, so okay, Shivam, I have this thing that P into Q equals constant. That means X into Y equals constant. If you plot this thing on the graph, what will it give? You
No,
tell
it
me.
will not give this thing. It will give a rectangular hyperbola.
Yeah,
That.
asymptomatic,
Hmm.
asymptotic lines in
Yes.
first and third
Yes.
quadrant.
Yes. 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 Not at
So
first
why don't they?
quadrant. Why would it be a
Okay,
first and third quadrant? Mm,
they will be an, if the right hand side is positive, say E is positive, and X and Y equals E, then either it will be in first quadrant or in the third quadrant,
yes.
because
Yeah. Yeah. I got your point. Yes. Okay. Now. Good.
okay. So
Either of the two, not two together.
yeah, either. Yes, sure. No, no, wait a second, wait a second. See, either both can be negative. Okay, both can be negative. For x
Yes.
equals negative and y equals negative, there will be a graph, and there will surely be a graph. If you plot
Yes.
four
It will be a
quadrants,
rectangular hyperbola in the third quadrant in that case.
yeah, in the both quadrants, it will lie. If x and y, the product of these two equals some
Oh
positive
yes.
constants,
Yeah.
then a
Yeah.
graph will be
Yeah.
there in the
You're
first
right.
quadrant as well as in the third
You
quadrant.
are right.
But
You are
if we say
absolutely
that xy
correct.
equals minus of something, like xy equals
You're
minus of
absolutely correct.
some,
Yes. I was
then
wrong.
in the second and fourth quadrant,
Yes.
in that case it will line for second and fourth quadrant. Okay, that thing is weird to you also, I know very well. So
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 this
I
is
was saying that
definitely
okay,
not
the
P into Q, isn't it?
yeah, yes, that is the thing I'm talking about, that these two are not being product, they are not being multiplied, there's something else.
If it's a
And
surface
what they're
of,
saying,
if it's a
yeah,
surface of, circumference of a circle, let's say, in that
hmm
is definitely equation. This energy, this Hamiltonian in the first line of this paragraph,
hmm
Hamiltonian,
hmm
दिखा ना? This H will be
hmm.
um, this H will be a function of P and Q, quadratic function in P and Q,
Yes, exactly,
and therefore
exactly.
it will describe the
Hmm.
circumference of a circle.
Circle, bilkul. And it will have an, the radius of equals to E in that
Yes,
case.
constant
And
value. Yes, because it also
yeah,
E remains constant.
yes. So instinctively, it gave me the idea that it's nothing but a circle. But you, okay, pointed me very nicely that, okay, the circle's equation is something different. It's not the product. But then again, I'm saying that, okay, the product of these two should give a rectangular hyperbola. But the surface seems as a circle. Now, how can we think of this? Like, let me change the page. Let's see if we have something next page. They haven't discussed much of these.
I think we can
Let
just
me let me read
discuss
this.
this thing
Hmm.
on our own because it's very straightforward. It seems. Um, if it is a circle, you must remember what could be the equation if it is a circle. What could be the what could H be as a function of P and Q? That is what I'm asking.
Now,
H B as
surely,
a
for
function of
sure,
P.
it should
Huh.
be in the form of a q square plus b p square plus
Huh.
c. Okay.
Yes. Okay.
Actually, it should not be c. It should not be c. I should say it should be
Yes.
ap square plus b p square, and a and b can be any constant,
Yes. But
real values. Okay.
precisely, if we consider pure classical mechanics, in that case, what will it be? It will be P square by 2m, right?
Mm, yeah, yeah,
P square by
right.
2m. That is kinetic energy
Yeah.
plus
Right.
k by 2, that will be the constant coefficient, into q square.
Exactly, Shivam.
Yes,
You are dead right here.
yes. So half k q square will be the potential energy.
Yes. Yes.
2m will
Yes.
be the,
Yes. Yes.
and therefore we have a Hamiltonian.
Perfect.
And this is what the
This is
circuit is.
exactly what
Yes,
you're perfectly right. Give me a second, right?
sure.
Can you hear me, Shivam?
Yes, I can hear you. You may continue.
Sorry for the disturbance. Uh, yeah. So I was saying, yeah, you're perfectly right. You know that why I was having this, thing that it should be sphere. Let me put your words into proper printed words. I have this thing. I have this thing. This one-dimensional oscillator. The best thing I have read today. Yeah.
Best thing that you read today.
Yes. Yes. It
Yes, there
gave me,
you go. There you
goosebumps.
go.
Uh, so I just want to read this for my whole heart. Okay. I just love this idea.
Wonderful. It's
So
beautiful. X square, then
because
we see a v square. Wonderful.
yeah, and you know what? This is not a sphere. This is an ellipse.
Oh my god, that's wow.
Yeah, this is an ellipse. This is not a sphere.
Ah,
I should read this. I should read this, and you'll get a very
yes,
good idea.
sure,
Okay,
sure.
Shivam. Okay. So one-dimensional harmonic oscillator. Now let's consider a simple harmonic oscillator of mass m and oscillating freely with the frequency nu.
And this
Okay, we
belongs to
have
the
one.
same chapter, is it?
Yes, Shivam. Yes. See,
Wow,
we are having this division of phase space into cells. Okay, we're
wow.
just on this point. Okay, the
Read, read,
gamma's
read.
phase.
Go on.
Yeah. So yeah, this is the application. This is the application of this whole lot what you have studied. Now let's see.
Yes, sure.
We are having a simple harmonic oscillator of mass m and oscillating freely with the frequency nu. Let's calculate the number of phase cells in the energy range from 0 to e, Shivam. Okay, with the use of energy of that uh, oscillator, we are tending to have and need to have to find out the phase cells, the number of phase cells present. Now the phase diagram contains one position coordinate. We have just limited ourselves to the one coordinate x and one coordinate p. Okay, simple. So it's a plane in p and x axis. At any instant, the total energy E of the oscillator will comprise of potential energy and kinetic energy. Now this thing we very well know. We know very well. So E is Pe plus Ke. Now potential energy of a oscillator is half Kx square. Hmm. And the kinetic energy is half mv square. This thing we know very well for any given harmonic oscillator. In case of a spring system, we have K is the spring constant, right?
Sure.
So now what we have done, we have put mv square in terms of p square. So 2e equals kx square plus p square by term, p square by m. Sorry. Now we have converted this equation in such a form that x square upon 2e plus k plus p square upon 2m e is equals to 1. Now this is a very simple equation of an ellipse of this form: x square plus y, x square upon a square plus y square plus b square square 1, where a is the
Give me a
semi-major
reason
axis.
why it is an ellipse and not a circle.
Shivam, an ellipse is a locus of a point which is equidistant from the sum of two points.
Yes.
You know, it is the definition of ellipse. So mathematically, when we plot, when we solve this thing, that okay, from two specific points, the distance of a point should remain the sum of the distance of the
Again,
point from those two.
in the case of circle, you have the same definition because
Circle
circle
is
is a special
nothing.
case of ellipse.
Yeah, exactly,
So I want you to
exactly. So
ask.
what
I
we,
want to ask you, how have
yeah,
you generalized my idea of circle into the book's idea of an ellipse? What is that generalizing factor in the equation? What thing is changing? Because
you
certainly
see.
because certain
Sure.
um, whenever we have a circle, we have
Hmm.
this equation सबसे नीचे वाला x square by a square plus y square by b square is equal to 1. Okay, can you see this equation I'm pointing at?
This is equation of ellipse, right?
Yes. So the only difference in circle and ellipse is a and b is equal to 1 in the case of a circle.
A and B is equals to A in that in circle. They both are equal,
Yeah,
nothing else.
yeah, yes, definitely, yes.
Hmm. So
Yes.
these are equal. Now you know what this
Mm.
result, what we are having this on the screen. This is
Mm.
derived from the fact that we are having a locus of a point. Okay, basically the whole idea is having the
No,
locus of a
that I
point.
know. I know the mathematics of what I'm asking is what is
I'm unable to get your question right then.
what is the physical parameter, okay, that is making this an ellipse? I think it is the variable in k. The k is not a constant quantity in this case. I think that is why the a will change. Don't you think so?
No, 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 Shivam. No, we
Hmm?
don't need to change
Because the
K
overall
for
energy.
A.
Listen, but if तुम मुझे बताओ, I'm not unable to understand.
No, Shivam. Yeah.
A and B different
Okay.
things. A and B are different.
A and B are two different quantities. Okay. They are uh, having dimensions same as X and Y for the sake of dimension analysis. That's that
Yes,
thing
of
you
course,
can put
of course.
aside. Okay. But see, we need to have A and B as constants. They can't be a variable. If they are changing as X and Y are
Yes, yeah,
changing, then
yes,
it won't
definitely.
become an
So
ellipse.
yes, you are. This is clear. This is clear that they will be a constants. They will be their constants. So my
Hmm.
question is, why are they different numerically?
Why are they different? Because because in this case the potential and kinetic energy are not same. In this case these energies are not same. And
Tell me. In the case of a circle, okay, so circle
uh-huh.
harmonic motion, of course, a
Okay.
very idealized, simple harmonic motion. So in that
Hmm.
case, at every point,
Hmm.
will at every point on this phase space, will the potential and kinetic be the same? Every point
Sorry.
on phase space, will it be
Okay.
same, kinetic and potential? Every point on that
No,
circle.
no, on the circle it won't be same, on the circle they won't be same
That is what
because
is happening here also, no? That's what you said. A and B, they are different because kinetic and potential are different, right?
yes.
Yes. So what I'm asking you is, in the case of circle, A and B are same.
Yes, sure.
Yes. Um, but in the case of ellipse, these are not same. The reason
Yes.
you gave is kinetic and potential are different here.
Yeah.
So I'm saying, well, in the case of circle also they are different, isn't it?
Okay. In case of circle, the relation is different. Na? Overall, the relation between these two is different. Okay. Um. For the thing you are asking me, see this equation. This E equals half kx square plus half b square by 2m. This half k and this 1 upon 2m. These two parameter have to have be equal. They must be equal for this to convert into a circle. That is mathematically true. Na? We can form a circle only when the coefficients of x square and y square should be equal. Only then
So let's
then a
put
mathematical
A
equation.
square and B square equal. Let's put them equal. Let's see what happens.
If we are putting them equal, that means Shivam, what we are doing is we are doing that half k square plus 1 upon 2 of m. The
Yes.
square of these should be equal.
What will happen? What
Are
will
you
happen?
getting this thing?
Yes. K will what?
uh,
M.
Let me tell you one thing that their magnitudes can be equal because dimensionally these both are different things altogether. You know, k having different their magnitudes can be same. Now if this thing becomes equal, that means k square equals 1 upon m square. That means k square the product of these two becomes 1.
Ah.
K square m square equals 1 will be the relation. So let me okay Shivam, this thing can be true. This thing can be true. You know, in if we have a particle, okay, say we have a particle for which the mass is just the reciprocal, the magnitude of
Yes.
mass is just the reciprocal of the magnitude of force constant.
Yes.
Then in that
Now,
particular case,
uh,
in that particular
the
case, this
circle.
ellipse will
Yes.
convert into a circle.
Yes. Now, my point is, let's define K. How will you call K? Because I think K is the um, a factor that stops a body from moving away from mean position. A factor that stops the body from moving away from mean position, right? And mass is something that I would also say, Arpit,
I'm missing
let's
you.
let's define this thing in terms of motion and rest. Okay, so I have a definition. K is a factor that pushes a body to remain in rest. Okay,
Okay.
the body to remain in rest in the mean position. If it tries to move to the right, it pulls it back. If it tries to move left, it pulls it back. So this is something that wants it to remain in the equilibrium position. Do not move. This is telling the body. Do not move. Do not move. K is telling. M is something uh, because it comes in kinetic energy expression. I would say that it is something that asks a body to keep on moving.
Okay.
Since it appears in the expression of kinetic energy, and M is something that is asking you to keep on moving. So we see that there is an inverse connection. I'm not sure up to what point I'm correct with my argument, but it sounds very, very intuitive. And that's why we have an inverse connection between K and M, and the product of the two is,
Yeah.
don't you see?
Yeah. Okay. The beauty of your words is that your thoughts is that you can connect any mathematical expression into beautiful words. Okay, this thing I am very sure that you saw that. Okay, k square equals 1 upon m square. That means they must have inverse relation in real sense too, and you put that
Yes.
very nicely into words, Shivam. Good, that thing is very
Thank
nice.
you.
And I want to
But I'm
have
not
yo
sure. I'm not sure.
okay, yes, I can give a very I want to add one more thing, that what is m. Okay, what is m is nothing but inertia, inertial mass. The inertial mass means that either it wants the body to have that constant speed. Either if it has some velocity, then m says that okay, you are moving with v velocity, keep on moving with v velocity. If the substance is staying at zero velocity, then the mass will say, the m will say that okay, you are staying at rest, be at rest. So see, this m is nothing but inertia. So you are right that okay, if it is moving, then it says okay, move on. But if it's there's no velocity, then it would say that okay, stop and don't move. Whereas k, for k I would go mathematically, f equals minus of kx for an expression in a simple harmonic oscillator, right? So the magnitude of force applied is the negative of the product of k and x. So greater will be the x, greater will be the force of a negative sign, keeping that object towards the central point. It wants that the particle should
Also, yeah, I
come to
would
that
like
mean
to
point,
add a little
Shivam.
bit more. Huh?
For x, for k uh, I'm little unsure. Just think that is just the factor, which says that okay, I will pull you more closer, or I will push you more, you know,
I would like to add
away
a
from.
bit more. I will say that
Hmm.
mass is there, of course. It is intrinsic to the very body,
Yeah.
the very body. It is intrinsic in it.
Hmm.
उसका अपना है ये आजन्म. But K
Yes.
that is being applied on the body by an external agent. This is, of course, the
You
case.
think so?
Yes, of course. The spring is pulling the body back. The body is, of course, a mass, and K has nothing to do with the body itself. Body's intrinsic qualities, its mass, its shape, etc., has nothing to do with K. K has no relation with it. K is an independent spring constant, an external agent,
Mm-hmm.
whereas mass is the
Hmm.
intrinsic to the body itself. So,
Can we consider the mass of the spring itself?
huh?
Hmm.
क्या?
हम कहते हैं कि हमने जो है we want the spring to oscillate. Okay, it will certainly oscillate. So we are pushing it, and we are just looking at the point which is the farthest most from the the point of the one point of a spring, and we have the hinged the second point. Now we compress it. Now we see that the point moves back and forth between the length. Now we don't need any external mass here. What do you think? We don't
Yes,
need any
so
mass.
that's
We can
why
just
that's what I'm telling you.
yeah.
K is completely independent of the body. If there is a body, it's all right. If there is no body, it's all right. But K is a force. It has nothing to do with the mass of the spring. It is
Okay, yeah.
it is the one of the property of the spring. Even if you don't have a spring, if you have a gravity, you know, so there is no spring here, but there is a kind of a force that is applied on the body if it moves, right?
The k the factor yeah, sure. The factor is just altering the magnitude of the force. The force itself is directly the the dependency of the force is see Shivam, see, let's go it in the mathematical way. We'll get to more close if you think. If you say f equals minus of kx, these two factors, the k and the x factor, are both are pushing it like, okay, the force will be more or less. It will depend on both of these two. But say if we don't have changing x, the x is um, say has a constant value, say 1. Okay, 1 is the value for x, 1 meters. We have placed a spring 1 meter from its mean position. Now when as soon as we release it, the force will be applied and it will oscillate.
Yes,
Say
definitely.
the now k we know is a positive quantity, as m is also positive quantity. Now greater will be the magnitude of k, greater will be the just the force applied to it. Okay, simply. So the greater will be the acceleration produced in the mass.
Yes.
Now say we have a if k is changed, you know
Yes.
no, wait.
And you are
In
right.
this
You are on the right
previous,
track. I can see where
no,
you're
sure.
trying to take me.
Yeah.
Yes.
No,
So
just before that, I want to say one more thing. But like as soon as we put a constant x and leave the system, the x keeps on changing. It won't stay to 1. As soon as we put it to 1 and leave the system alone.
but K
See
remains the same.
that.
Why do you think so?
Yes. The x is changing, whereas k is constant. K won't change now. So k if isn't changing, then it is an intrinsic quantity. Okay, that's
Yes.
good, but it isn't applying any additional thing. Na? It isn't giving any additional uh, force, or should say repulsion or anything on the system. Na? It
Yes.
isn't causing anything, I think.
Yes. Yes.
Okay, you have talked a nice thing on this, like k and m, the relation between these two. It's something
But
very
I
interesting to
think
note
when
about.
we say that Km, the product of the two,
Yeah.
be equal to one, uh,
Mm-hmm.
if you take a case in which the body is displaced 1 meter, x
Yes.
equals one, and then you keep
Yeah.
changing the value of K. let's say you keep on changing the value of k, right? So with change
Okay.
value of k, we'll have different sorts of oscillations, isn't it? Right?
No.
Because the potential energy will keep on changing. You see, the body is displaced by 1 meter. Let's keep it there only.
Mm-hmm.
Let's
Yeah.
there only. If we change the
Yeah.
value of k, we'll see that there will be
Mm-hmm.
the value of potential energy, isn't it?
Definitely. Bilkul.
Yes. So potential energy
Exactly,
will keep
Shivam.
on changing. So the oscillation the kind of oscillation will keep on changing, right? The mass remains constant, the position, the displacement remains constant, but the k has we are making it change. So there will be change in potential energy. Now what I'm trying to say is, if you want the oscillation to be restricted to a circle on phase space, okay? If you
Mm-hmm.
want the oscillation to be restricted to a circle only on a phase space,
Mm-hmm.
and given that you are changing k, you have to vary the value of m such that their product equates to 1.
Mm-hmm. Yes, sure.
So the
Definitely.
most important condition here is that, well, we want a circle on the phase space, isn't it? E-
Yeah, that's your
in
desire.
that
Yeah.
case, km must be equal to 1. Okay.
Yeah.
If it's not a circle, it could be anything else. It can be any other number. There is no, we can't say km equals 1 if it's not a circle. So for circle, we want this thing to happen. I think it's
Mm.
pretty much clear now. What about you?
Yeah. Okay. Okay. Nice. Nice. You took the discussion into very, you know, imaginative sort of, you know, desireful and imagination. It makes both of the things in this. You know, like we are having k and m is equal, and then we can have this ellipse converted into a circle. You know,
Yes.
and for that particular purpose, we need to k and vary
Yes.
k and m
Yes.
as per requirements.
Yes.
Nice,
Yes.
nice,
Yes.
Shivam.
And there has to
I
be a
really wish
validation. Mm-hmm.
I really wish that this things also happens in real world. You know, and we can have a circle. We can change this book, and in place of the ellipse, we can have the equation of a circle. That thing. Hmm.
Generally, if k and m are not varying according to the relation km equals 1, okay,
Mm-hmm.
if k and m are not varying according to this relation, then it will be everything. It will definitely will be an ellipse. It will not be a circle.
No, Shiva, I'm sure one more. No, see, one thing is there that we don't need to vary them continuously, na. We don't need to vary them continuously. We just need to give them
Yes,
assign them a
yes,
value,
yes, yes,
which
yes, yes,
through which the product remains constant. We don't
yes.
need to have dm and dk have a value, because dm can't be a value in the
We
case
don't
of
really have to
electron.
change. We don't really have to change. Why?
Yeah.
Why I'm taking this word? Why I'm taking this word
Hmm.
change? Because I'm considering different cases. So if you have a spring of spring constant equals half
Okay. Okay.
half
Okay.
units,
Yeah.
and you have a
Yeah.
mass that is 2 kilograms.
2 kg. Yeah.
Yeah, so
Definitely.
this will definitely will always be a circle, regardless of what you do, whether you change,
Yeah. Exactly.
regardless of everything else, it will always be a
Exactly.
circle. If you have one
Hmm.
fourth the value of mass
Mm-hmm.
and
Hmm.
fourth units the value of k, again you will have
Hmm.
circles. That's what I'm. Um,
Mm-hmm. You are clear about all these things. Very good. Now, Shivam, let's continue this discussion, and we'll get some good result from
yes,
this.
yes, of
Okay.
course. This was wonderful, by the way.
Okay.
At least I
Yeah.
got to remember certain new relations and see things from a very
Yes.
different perspective.
No, I must say that you put the mathematics in words very precisely and very correctly. Okay, that thing I really like. Now, I should move ahead. So this
Yes,
relation we
sure.
have come across, that is x square upon a square plus y square upon b square equals 1. This is a proper equation of an ellipse which have a major axis as under root of 2e upon k and minor axis as of under root of 2me. Okay. These two are major and minor axes of the ellipse. Now let's see how the ellipse looks like. Okay, so on the p axis we have a minor cut, which is at under root of 2me, the minor axis. On the q axis, the actually the x axis, we have under root of 2e upon k, the major axis. Now on the surface of this ellipse, the energy is constant. This is as equi energy surface. As we have equipotential surface, we have this equi energy surface of this ellipse. So I should write this thing. This equation represents an ellipse in x and y, and the points constant. The points of constant E lies on this ellipse. Okay, so having major and minor axes this and this respectively. Now for energy range from 0 to E capital E, the area is A equals pi AB. We have product of these two as 0 on the origin, and all the area inside this ellipse is the area having energy from 0 to E, right? Now the area, the phase area of this entire ellipse is pi AB. Pi times uh, length of major axis into the length of minor axis. This is mathematical. The area of an ellipse is given by this form. Okay, we have a derivation for this, at how the area of an ellipse is
Of course.
found out. Hmm.
A
Yeah.
generalized term of
So
pi r square. Yes.
yeah, exactly. Pi r squares. Yeah, definitely. Like b will become a and it will become pi a square. Same way. So that is pi times. So we have a equals this and b equals this. Now the area under this ellipse is coming out to be 2 pi e under root of m upon k. Okay. This thing we need to remember. And then each phase cell has an area of qi into pi. I should say xi into pi equals h naught Shivam. Okay. We know this thing. We have been studying this. Qx in d, like dpx into dpi equals h naught. So for considering this as a phase cell, we have we are considering this Shivam as a phase cell. You see. So hence the number of phase cells in energy range from 0 to E. This whole was a phase space, and inside it we have covered an area of energy 0 to E. Now we want to know how many phase cells reside in this area. We'll count that. This phi E is the number of phase cells in energy from 0 to E, the number of phase cells. And this is what? This is just uh, this product, the area, divided by H naught.
Yes.
Whole area divided by H naught. Why? Because this whole
Definitely, I
area
got it.
represents the
Yes.
area of. You got it? Okay. The H naught is the phase cell area. So number of phase cells can be determined by this. Just a minute, Shyam. Just a minute.
Yes, sure.
Hello. Hello. Can you hear me?
Yes, I can hear you.
Okay. So now phi E is the number of total phase cells present inside this area, and this is given by this equation. I know you know this. Now the frequency of a simple harmonic oscillator Shivam, you know this, that it is given by mu equals 1
Sure.
upon 2 pi
Yes.
under root k by m. You know,
Again, K by
we
M.
know
Hello,
this
K
equation.
by
We have
M.
under root k of k by m. Okay. So this k by m thing, is something we have been talking about. So, okay, never mind. So this nu is fixed. This thing we know. Now we are just substituted this value in this particular equation of phi e. So phi e becomes e upon h naught nu Shivam. Okay, this equation I think clear. So what it is achieved here at E equals h naught nu times phi e. H naught nu times phi e. Now phi e, as we have discussed here, is the number of phase cells. Now being a number, it has to be of integral. It has to have an integral value. So it can be either 0, 1, 2. A number of phase cells can't be a fraction, can't be a irrational number. So what we get from this equation, that E equals n h naught nu. This means that energy can occur in discrete states and has values integral multiple of h naught nu only.
Hmm.
So basically we have seen that okay, any particle can have can oscillate in one dimension, and basically it will have energy discrete, and it should be in relation with its frequency given by equals n h naught nu. In this case,
Uh,
they have assumed this as h naught because we are classically determining all these things. But
it's an
when it comes to
arbitrarily small
quantum, it should
quantity.
definitely, yeah, it's an arbitrary quantity, but it's a very small number. We know that only as of now. Okay, Shivam. So
Yes.
this, I think, this is very nice because we have got an ellipse through which we
Hmm.
can have this energy surface, and by that this phi is very special thing, that the number of phase cells. We'll use this later on, and I think for today, Shivam, it should be fine.
Hmm.
Discussed many of things, and